So hello everyone. My name is Paula, and this is our project team. So I would like to thank you everyone for contributing. And our project is about SST prediction using deep learning models. So basically, our interested area was this region, and why to predict SST. So SST impacts weather, and it's really important to measure that for marine ecosystem, especially in motion affected regions. This is a strategic location that encompasses crucial parts of Indian Ocean, Arabian Ocean, and Bay of Bengal. And there is an ecological importance about rich marine biodiversity, coral reefs, and significant fishing zones. It's quite important to understand the variability for cyclones and hurricanes, which might develop, and predict areas of high productivity or potential fish immigration, and also to monitor changes in ecosystems due to warming or cooling trends. So our objective here was to predict SST spatial distribution for the following day, training a deep learning model using two data sets. So we were basically using ERA5, reanalysis, and World satellite data from NASA. So as I mentioned, our data sets are these two, and here you can see the time period and also the area of interest. And the methodology that we used is the convolutional LSTM, deep neural network, and we used the Python library called TensorFlow. And we are using a window size of 5 days, which means that we are basically giving to the model 5 days of input, and we want to predict the following day. And to evaluate the models, we are using the MSE.
Yeah, so first we use the ERA5 dataset to test the model. The model architectures we include for the ERA5 dataset are transformer, convolutional LSTM, and the combination model that combines convolutional LSTM and transformer layers. And we also did fine-tuning with the layers, parameters, amount of input data, loss functions, and window size. So for the transformer architecture and result, in natural language processing, transformer has two mechanisms. One is self-attention, one is sentence-to-sentence prediction. Here we embed the self-attention in the multi-head attention layers. And you can see the validation of MSE we got at the very end is 0.19. And we also compare the MSE between the predicted output and true output, and the MSE between the last input frame and the true output. If the former one is smaller than the later one, then we say the model is very proficient. And here is the convolutional LSTM architecture and result. The validation MSE at the very end is 0.027, and the MSE between the predicted output and true output is 0.04. Here is the combination model architecture. The validation MSE at the very end is 0.04. But this model is GPU demanded. It takes 50 minutes for each epoch if you're using 16 CPUs. And it needs 128 gigabytes RAM. So if you want to reproduce a model, you have to train it for your speed. So, and here are the result summary of using the ERA5 dataset. And you can see, although the convolutional LSTM and transformer combination model has potential, it's very computationally expensive. So we recommend using the convolutional LSTM, which has a smaller validation MSE.
Yeah, and based on this result from ERA5 data, we want to use more high resolution data from satellites. And we use convolutional STM model, and also Australian folks did 3D convolutional neural network. Yeah, so here you can see the result from 3D convolutional neural network. Yeah, as you can see that some problems with post-processing data, so that's why the MSE between predicted output and true output is relatively high. And yeah, so, and our best version of our model is convolutional STM using satellites dataset. And you can see that validation MSE is quite small, but what's more important, MSE between predicted output and true output is smaller than the MSE between last input frame and true output, which means our model is gives us better predictions than if we use just the previous day to predict the following day. And yeah, here you can see some small GIF animation with predicted output, true output, and difference between them is was using mirror data set using convolutional LCM data. So you can see the general structure is kind of the same, but still a lot of differences between them. Red color in the last picture denotes that the model overestimates temperature, and blue notice that it's underestimated.
So basically, comparing the models, we could see that if we use the more satellite data, we were able to get a good MSE value for the convolutional LSTM. Although if we compare with the ERA5 reanalysis, you can see that the value for MSE was lower. But something that we need to keep in mind is that the Moore data is higher resolution data, and we could solve a smaller scale physical process with that. And also the MSE differences in model predictions showed by Boris and Jurai were smaller in Moore data. So that will be important to understand seasonal changes. And also it means that the input when we give to the model, it's returning a better result, a better output, and a better forecast.
Yeah, so here's the pipeline. So once we get the predicted image from our time series model, which is convolutional LSTM, we do post-processing, which restores the image to normal SST image. Then we pass the image to the classification model. For example, if we want to detect phenomena such as upwelling, we want to build a classification model to detect upwelling using the convolutional neural network architecture, for example, efficient FD0 after fine-tuning. And if we remove the top layer, we get a float number between 0 and 1, and we detect upwelling using that float number and by setting up a threshold, for example, 0.5. And here is our classification model for a two-dimensional image. To predict upwelling, we use the efficient FD0 architecture, and you can see the final accuracy 0.97. And as the upwelling event happens most frequently in summer, the prediction also centralized in summer months.
So basically, some challenges about this project was working and communicating in different time zones, as we have Australian guys working with us and also virtual people, and training and running a deep learning model with 20 years of data and low memory machines. And also we have some achievements. So it was nice, and we could see that everyone was actively working in the project in Seattle, in Australia, or virtually. And also we shared and discussed and improved Python fonts together through GitHub. And some people run the first time for the first time a deep learning model. And some of us also learned how to use the Python library PyMD to work with the Moore satellite data. The guys from Australia did that. And we were also able to assess and running the model in powerful virtual machines, which allow us to have better results at the convolutional LSTM using the Moore data. And thank you, and acknowledgements for the guys.
Thank you. Do we have any questions?
I have a question. Yeah, I don't know. It's like for deep learning. It's like a deep learning question in general. Like for instance, we are using ERA5 to run our model, and we realize that ERA5 doesn't quite capture the peak of hurricane winds. So how does error propagate if you make use of a data set that that initially it's like maybe it has some errors, then you use it to run a deep learning model? What would be the result? I'm just quite curious.
That depends on the architecture of the deep learning model. For example, the feature extraction of transformer layer and the feature extraction for the convolutional 2D layer are different. So if you are using different data sets, you also have to adjust the model architecture and do benchmarks and fine tuning to fit that data set to the model. So I would say that depends. Yeah, but typically if you use time series data, the convolutional LSTM is the best choice. You can use that kind of architecture.
I have a related question. When you show that the mismatches or the error picture, the arrows have structures, right? And it seems to be specific structure elements in that particular comparison. And because this is a deep learning model, I guess this is more of I just wonder about your comment in terms of this type of model is learning from data and then look back for 5 days or 4 days, whatever the time window is. Its ability to capture sort of at least the physics that are being captured in the model data set that is given. So it's sort of following up on the previous question on that.
So, which mechanism capture the features, right?
Or like the ability of the model to capture the mechanisms that are actually captured in the physical model.
Yeah, so the convolutional LSTM is designed to handle the time series data, for example, like n days. So it has layers to capture the spatial and time relationship. And if we are combining transformer layers, the self-attention mechanism from transformers can capture the global dependency. For example, a too distant data point, the convolutional LSTM cannot handle that. They can handle relatively regional or locally data points, which means they are very close. So that's the limit of the convolutional LSTM. But for transformers, for example, they can capture the relationship between two distant data points.
I have a question about like the machine comment. So, can you go to the slide where you're talking about the machines and which were CPU friendly? Yeah. Yeah. So, keeping in mind that an environment and what you learned about that, what do you think is like? It looks like you do for doing stuff like this and doing it in a hack week, having a GPU would really be important.
If you are running two-dimensional, if you are running model based on two-dimensional data, which you don't include time, right? Because we're using past 5 days that include the time channel, time dimension. I would say CPU is enough to handle two-dimensional computation, but if we're using additional dimensions, then GPU would be needed. And the whether you are using CPU or GPU, that only influence the speed you're training the model. If you are using another dimension, you have to also increase the RAM, otherwise you will get a crash.
Okay.
Alex, one of the team members, he developed a script that it's possible to running low memory machines. So that's really good. But I was testing, for example, in Jupyter Hub, and we need a bigger data set to be able to make better results. But it is possible also using like dividing up your study area in small pieces and then running the model in for each one of these areas. So you reduce like your memory, your needed memory.
Okay.
Yeah.
I have a similar question on that sort of topic. Were you guys using a VM or something that was purposely provisioned for machine learning or not? Because that will change the sort of like CPU requirements in that way.
Yeah, we are just using the Jupyter Hub virtual environment, but we have the access to some supercomputer that supports GPU. So yeah, and you can also run that in Google Colab. They allow you to use their GPU or GPU. That would help, but the limit is you have to load the data into Colab without getting a crash.
Yeah. So
Yeah.
did you like you chunk it? Like
We did data pre-processing, I mean, but we can.
Yeah, so the script that Alex developed is using chunks. And we have the script in GitHub as well. We put like in the final scripts folder. So we have like one version of the script using GPUs and another version of the script that can be used in low memory machines or even in high memory machines. So, but he's using, if I understand right, if Alex is here, he can comment maybe.
We can probably take this offline, just to respect everybody's time. Sorry, Joseph, go on.
No. Well, thank you, everybody. That was the last presentation of the day. If we can just give another round of applause for everybody and everyone's very successful projects.